electrical field from charge distributions, and we wanted to do one last example before we moved on to Gauss's law and the postulates of it. So the example we were dealing with was an example of a cloud. And in the spirit of approximation, we approximated that cloud as a cylinder. In the spirit of approximating a cow as a spherical cow. Right, and then because it's a cylinder, we can use cylindrical symmetry, and so we can use cylindrical coordinates, right? And then this is Z, okay? And then there's of course the angle phi, right? So it's going to be R phi Z prime prime, because those are the coordinates of the material itself that is the source of the electrical field. And the idea is that what would be the field at a point P just under the cloud? Well, again, we have to divide this cloud into a bunch of volume elements. So let's say there is a small volume element, and we said in cylindrical coordinates, the volume element has volume. So dV in cylindrical coordinates, dV prime. Remember, this is source, so I always have the prime. Is going to be R prime, dr, dphi prime, dz prime, right? This is the volume element. This is a volume of one infinitesimal, one tiny volume. And this is going to have a charge rho v. So assuming that the cloud has a charge density of rho v in coulombs per meter cubed. So this is going to have a charge density of rho v. So the charge in this volume element is going to be rho v dv prime. Okay. The question is, what is the total field? The total field is an integration over the whole volume. But there's also another thing we have to factor in, which is make use of the symmetry of the problem. According to the symmetry of the problem, the distance here is r, call it r. This distance, first, how far away we are from the center of the cloud. Let's call this distance h. And then the coordinate, the z coordinate of the volume element is, let's call it z prime, right? So the point where we're calculating the field is at minus h. So that's h is how much meters we are below the center of the cloud, and then 0, 0. Right, this is the coordinate of the point we're interested in. And then the field is going to be dE. This is what can now see my screen. I thought they were able to see my screen always. Anyway, probably a laggy interface, right? But the point is that there's a symmetry here. So if I have a second volume element here, that will introduce another dE here. So the tangential components are going to cancel. And what will remain is the normal component, den. So as we integrate, all the tangential components are going to cancel naturally, and what we will remain with is the normal component. So really, we only need to sum up the normal component to get the total field, because that's, if we do that we simplify matters a little bit in the integration. So this is going to be z prime here, this distance, and this is r, of course. This is, let's say, angle alpha. Alpha varies depending on where we are. So what is dE in this case? dE as a magnitude is going to be rho v times the volume element r prime, dr prime, dphi prime, dz prime, right, over 4 pi epsilon naught r squared, applying Coulomb's law. So it's going to be rv, r prime, dv prime, dphi prime, dz prime over 4 pi epsilon naught. Instead of r, what is r? I can use the Pythagoras theorem, right? R is going to be, what is this distance here? This distance is r prime. Oh, and by the way, that the radius of this cloud is b. Okay, but the distance from the origin to the radial distance to the volume element is r prime. right? So this distance is r prime, this distance is z prime plus h. So using Pythagoras theorem, r is just r prime, r squared is just going to be r prime squared, right? Plus h plus z prime squared. Okay, and now we said we don't care about dE, we care about dEn, the normal element. How do we find the normal component? The normal component is just going to be, so this is alpha here, right? This angle is alpha. It's just going to be this component, the radial component, times cosine alpha. So this has to be multiplied by cosine alpha to get the normal component. What is cosine alpha for this triangle? Cosine alpha is the adjacent distance, z prime plus h, divided by the hypotenuse, which is r, which is this r prime squared plus h plus z prime squared. Yeah. So this is going to be yeah, that's what cosine alpha is. So we're going to have let's see. Oh, yeah, square root. So this r is going to be, so it's going to be z prime plus h. So cosine alpha is going to be z prime plus h over this thing square root. So it's going to be, so x plus times x square root is x to the power 3 over 2. So there's going to be a power 3 over 2 here. Okay, Newton per coulomb. And this now we integrate over the whole volume. So E, total E is going to be the integration of this thing. And E from inspection, this is going to be pointing downwards. So this is going to be in the minus z hat direction. And this is going to be a triple integral. Let me first take all the constants out, just to simplify. So if you take all the constants out, I'll have rho v 4 pi epsilon naught, and then triple integrals of r prime, dr prime, dphi prime, dz prime, r prime, z prime plus h over r prime squared plus h plus z prime squared 3 over 2. D, let me see, what should the order be? Let's do dr prime, and then let's do dphi prime first. Dphi prime, dr prime, dz prime. Okay, so that's the integral. R goes from 0, phi goes from 0 to 2 pi. It's a cylinder. We're integrating along the whole cylinder. R goes from 0 to B. That's the radius of the cloud. Z goes from, oh, I didn't talk about the length of the cloud. So this is A from the origin to the top of the cloud is A, from the origin to the bottom of the cloud is A. So this goes from minus A to A. So this is the integral that we're going to try to find. Of the top, d phi is easy. Nothing here is a function of phi. So I can remove this, and just multiply by 2 pi. So this becomes pi goes away, and we end up with 2 here. Okay. And then we need to multiply with respect to r prime. R prime is a little bit, I guess, I mean, let's do it. So the integral of r prime z prime plus h over r prime squared plus h plus z prime. Here you can go to an integration table, or you can, if you're using software, you can use a computer algebra software to try to do this integral, but this is easy to do by inspection. I mean, this is whenever you have something like this, where you have a squared power in the denominator and a first order in the numerator. This is easy to do by inspection. You can even do substitution if you want. But I mean, this is going to be what happens if you differentiate x over x squared plus a, d over dx, right, to the power square root. Let me see. Yeah, square root. What happens if you differentiate, sorry, not x, a, differentiate this square root. So whenever you see something like this is the first thing you should try. Okay, what happens if I differentiate the square root, reciprocal square root? If I do this, because this is easy to do, this is going to be, this is a quotient. You can use the quotient rule. The denominator, x squared plus a. So it's the denominator times the differentiation of the numerator, a is 0, right? Minus now square root. Oh, a times the square, the differentiation of the square root. So it's going to be 1 over 2 x squared plus a, plus you differentiate what's inside the square root. It's going to be 2x. So the 2 is going to cancel with the 2, and you end up with x. So I'm trying to show you that this arises naturally whenever you have x over square root. Let me see, but there is power 3 here. Is this right? Did I do this right? Let me see. So yeah, this is going to be 0, and then it's going to, oh, okay, the quotient rule, of course. So there's an extra, this is what gives me the power 3 over 2. So the extra quotient rule is divide everything by the square of the denominator. So I'm not done with the quotient rule. The square of the denominator is x squared plus a. So this gives me the minus a, x over x plus squared plus a, 3 over 2. Okay, so whenever you see x over something, x squared plus a power 3 over 2, you know that this comes from, of course, I can take the minus sign to the other side, right? So the point is that this thing is equal to z prime plus h. In this case, it's a constant, minus z prime plus h over square root r squared plus h plus z prime squared. This is the integral. Now I'm trying to find this integral from 0 to b. Okay. So this I have to evaluate from 0 to b. Let me put the minus sign here. This is a constant as far as I'm concerned. I can take it out. H plus z prime, I can take it out. So evaluate this at 0. So let me calculate this. At 0, it's going to be minus 1 over h plus z prime. So let me keep this inside h plus z prime. So it's going to be minus h plus z prime over h plus z prime, right? So it's going to be oh yeah, no, this is correct. So this is going to be, I'm just wondering where the minus 1 goes. Oh, start with b, sorry. So at b, this is going to be h plus z prime over square root b plus h plus z prime squared. Minus becomes plus. At 0, so it's going to be h plus z prime over h plus b prime, so it's going to be 1, right? So the result of this integral is going to be 1 minus h plus z prime, or 1 minus h plus z prime over square root B plus H plus Z prime squared. Okay. So this is going to be this integral. So now E is reduced to minus Z hat rho V over 2 epsilon naught. And then I have the final integral, which is from minus A to A. I think there's a typo in the book there. And then, yeah, so this is O prime. So this now is integrated with respect to Z prime. 1 minus H plus Z prime over B plus H plus Z prime squared dZ prime. Now this integral is easy to find. I mean, the book goes through some weird thing where he has a logarithm there. I don't know why it does that, but this is a really easy integral to find. So this is minus Z prime rho V over 2 epsilon naught. What is this integral? Z prime. Z prime simply minus B squared plus H plus Z prime squared. That's it, right? If you differentiate this, if you differentiate Z prime, you get 1. If you differentiate this, you get 1 over 2 square root B squared plus H plus Z prime squared. And then you differentiate what's inside the square root. So this gives me 2 H plus Z prime, right? 2 cancel with 2, I end up with H plus Z prime over square root B, not B squared, B plus H plus Z prime squared. So this is easy to do from inspection. I guess the book went to some computer software and it spit out something that cancels out with logarithms. But this is a really easy integral to find. And this goes from minus A to A. And just plug in the answer. So E ends up being minus Z prime rho V over 2 epsilon naught. At A, this is going to be at A and minus A. So A minus A is going to be 2A. That handles that. And then I'm going to have something with plus B squared plus H minus A squared minus B squared plus H plus A squared. So this is the electric field, just an approximation of the electric field just underneath a cloud. Assume a cloud with radius, a cloud that is assumed to be a cylinder with radius B and height 2A, height of the cloud 2A. A distance h below the cloud, below the center of the cloud. So if you have a cloud approximated to be a cylinder, if you go a distance h below the center of the cloud, and the cloud has radius B and height 2A, then the field, normal field at that point is going to be this expression. Pretty nifty what you can do if you approximate things to be symmetrical geometrical objects. Okay. So this is an example. At this point, calculating the total field for any charge distribution is kind of going to be on the difficult, cumbersome side because you have to do a lot of integration. Essentially, it is an exercise in integration. And when we move forward, we will discover that many times we do not need to do this direct integration. We can use something called Gauss's law. But before we go there, I want to introduce what's called a new version of the electrical field, which is called the electrical flux density. This is nothing new. This is just a new way of representing the electrical field. So the idea is that, if you remember, the electrical field for a point charge, around a point charge was it's going to be R prime Q, the value of that charge, over 4 pi epsilon naught R squared. So this really epsilon naught is the way we introduce the constant. So there is a constant in Coulomb's law, and this constant depends on material. It was empirically found that if we try to find electrical forces, the forces depend on what material the charges are immersed in. If we are in air, that will be different than if we are in water. That will be different than when we are in complete vacuum. That will be different than if we are in some sort of material, right? So this depends, as you see, on the material or the medium. This depends on material, or I guess it's more accurate to say medium. Is an empirical result, and it factors into the definition of the electrical field. We could define another version of the electrical field that does not depend on the material, right? And the way we do that is we wanna make this equation just dependent on geometry, the geometry of the problem, the charges and the geometry of the problem. How do we do that? We can take this constant and we can take it to the other side. So I can take epsilon naught E, and then I can define this new quantity as the vector field D. And this, clearly we see, is only dependent on the charge and the geometry, on the charge and the distance away from the charge. So this D is called flux density. And the reason we call it flux density, I mean, just look, at first it's not dependent on the medium, right? And just look at its units. Its units are charge, so I have charge, Coulomb, and meter squared. So it is a density over a surface of some sort. So this has units of Coulomb over meter squared, right? And it does not depend on the material. This is what D means at this point. It's another way of looking, of coupling the material dependency with the electrical field to get a new vector field that does not depend on the material. Now, D has a deeper meaning that we will get to in time, but at this point, it's enough to understand D as just coupling the material dependency to the vector itself and getting a new version. Just depends on the geometry and the charge, right? And it is a sort of density. It's a density over area, right? So we can actually integrate it. If I take D and then I integrate it over a surface S, I get something called the flux, and this has units of Coulomb. So that's why we call it the density. It has units of Coulomb per meter squared. It's something distributed over meter squared, right? And when we integrate it, we get the total, it's analogous to flow, right? We get the total flow, which is the total flux. We call this the flux. Now, as I said, D has a deeper meaning. But this is how we're going to introduce it. So I want to, losing the dependency on material is nice, because now we can solve problems first with D. We can solve problems where we have multiple different kind of mediums, and we don't want to deal with the problem of we can solve the problem in general with D, which has no medium dependency. And then after that, we can find E in every point in space, depending on what the material is in that point in space. So, I'm gonna go through a typical example, textbook example, which is, so this is an example. What is the field? Let's say a charge has material around it. So up to a distance, let's say R1, the material is vacuum. So, by the way, epsilon is epsilon naught, right? Materials. By the way, vacuum and air have different epsilons, permittivities, but practically free air is really close to vacuum. So sometimes it's a good approximation to assume that a free air is equivalent to vacuum, but in reality, it's not exactly equivalent. There is a small difference, right? And then from R1 to R2. There is another medium with epsilon 1, which is larger than epsilon 0. And then finally, so this is material A. And then finally, this is material B. So it's a shell, right? So material B, which has epsilon 2, which is also larger than epsilon 0. And then we said that air is approximately epsilon 0. The question is, can we want to plot D with respect to the distance R from the center, and then E with respect to the distance R. So we know D instantly does not depend on epsilon. So D is going to be R hat Q over 4 pi R squared, right? That's what D is. So the magnitude of D, I just removed for the vector, right? Another way of stating the magnitude is removing the arrow from the top. If I remove the arrow from the top, think this is the magnitude of the vector. Okay. So this is the flux density anywhere in space, regardless of the material, right? So and notice it has this sort of inverse square. So if I want to plot it, it's proportional to 1 over r squared. How do you plot 1 over r squared? Something like this, right? It goes to infinity at r equals 0, and then it dwindles in an inverse square matter. Of course, this has the 4 pi and then q term, but it looks something like this. However, when you try to plot the E, for r less than r1, E is just going to be q over 4 pi epsilon naught r squared. For r larger than r1, less than r2, E is going to be the same thing, is going to be D divided by what? Epsilon 1. So it's going to be q over 4 pi epsilon 1 r squared. And for r larger than r2, is going to be D over epsilon 2. So it's going to be q over 4 pi epsilon 2 r squared. So E really is going to be the same as D, but only scaled by different values. So here in the beginning, it's going to be something. It's going to be something like this. And then once we reach R1, it's going to be suddenly scaled by a different value. So epsilon 1 is larger than epsilon 0, right? So it's going to be some smaller value. Dot. It's going to drop like this, right? And this is the original one for air. And then it's going to keep going down. And then when we reach R2, it's going to drop further. This is going to keep going down. And then when we reach R3, I guess, we're going to go back to air. When we go back to air, we're going to jump up and then continue going down. So there are going to be this discontinuities in the electric field intensity due to the sudden change in the material. Okay. So what's the other part of the problem? Calculate the electrical flux through a spherical surface of radius r. You want to calculate this. I mean, this is easy, right? The total flux over a spherical, right? It's S with radius r, d dot ds. I mean, we can use spherical coordinates in this case, I guess, because it has spherical symmetry. What is the volume element? So what is D first? D is, we said, r hat q over 4 pi. Now, this is going to show you the artificiality of 4 pi. The constant was introduced in this way just because the 4 pi is going to cancel, right? So this is 4 pi r squared, right? And then what is ds? ds is going to be r hat. The surface element is going to be r squared sine theta d theta d phi, right? That's the surface element on a sphere where r does not change, right? On a surface of a sphere. This is the surface element. So if we take this dot product, r cancel dotted with r hat is going to be 1. So you end up with the flux being the surface integral. It's double integral. So notice the r squared is going to cancel with this r squared. So you end up with q over 4 pi sine theta d theta d phi, and then theta is going to go from 0 to pi, and phi is going to go from 0 to 2 pi, right? And really, I don't need to do this. I don't really need to calculate this thing, right? Why? What I'm calculating here, this is a surface element of a sphere. Q and 4 pi is epsilon constant. I can take them out. What's left? What's left really a surface element of a sphere. Can I do that? Actually, let me not cancel the r squared. Keep the r squared. Right, and then I take the r squared out. What remains here? What remains is integrating the surface element of a sphere over the whole sphere. This is what? This is the surface area of the sphere. We know that the surface area of the sphere is 4 pi r squared. So this shows you the artificiality of the 4 pi. The 4 pi was plugged into Coulomb's law just to, just to kind of match that surface area of a sphere, essentially. So this cancels with this, and the total flux is just the Q. The total flux around the charge is just the value of that charge, which makes sense because the total flux has a unit of Coulomb and charge has a unit of Coulomb. So it will make sense that the total charge inside the sphere is going to equal to the flux around the sphere. This is going to turn out to be much more general than that. It doesn't have to be a sphere. It can be any surface area. And when it turns out to be more general, it's going to be called Gauss's law. Which is what we want to introduce next. So next we want to talk about electrostatic postulates, and that includes Gauss's law and what's called the circulation law. I don't know if it has a specific name, but what's called the circulation law. Gauss's law is the fundamental law. The circulation law is also fundamental, but I would guess that conceptually Gauss's law has a really deep-seated place in the subject. So the way we would go around this is we would use, derive from Coulomb's law, those laws, and then we're going to go backwards. We're going to say, okay, those laws are actually the fundamental postulates. And then we can derive Coulomb's laws and everything else from those two laws. So the idea is that I have the definition of the electric field intensity due to a point charge. So this is r hat q over 4 pi epsilon naught r squared, where r without an arrow is just the magnitude of the distance vector from the origin to the q charge, right? This is r. What happens if I take this point? And a point charge is really an idealization. Even if you have a distribution of charges, if you zoom out, this whole distribution is going to look like a point charge. So even when you have something that's kind of like wonky and distributed and not uniform, just keep zooming out, and it will turn into a point charge as far as you're concerned. So the question is, what is the flux of a point charge? We already solved that problem, right? So what is E dot ds for a point charge like this? The flux. Essentially, well, not the flux. This is if it was D, it would be the flux, but the flux of E, let's call it, right? So we can use the symmetry, right? E is this, and we have the surface element of this. So I can write E. So this is equal to r hat dot r hat ds. I'm not gonna write the surface element, right? Times q over 4 pi epsilon naught r squared. Right? R is constant, so I can take it out. It's going to be 4 pi epsilon naught r squared q s of ds. This is I'm taking a surface element on the sphere, integrating on the whole sphere. This is just the surface area of the sphere. This is 4 pi r squared. So this is going to be Q over epsilon naught. So for a point charge, the flux of E dot ds over a sphere, over a surface S, that's a sphere, is going to equal the total charge inside the sphere divided by epsilon naught. T, and then there's a sphere here. Right? S. Now the key thing here, the key concept that's going to lead to Gauss's law is that this doesn't have to be a sphere. This can be any surface, whatever it is. It could be like a potato around Q. And this will still hold. This will still be true. Right? It's a really fascinating result. And this is Gauss's law. And this, and we can prove this for a point charge. But once we proved it for a point charge, we prove it for everything. Because the field can be decomposed into components that comes from different point charges. If I have a distribution of charges, I can always, and using superposition, I can always decompose the field into components that come from every point. And Gauss's law is true for every point. So Gauss's law is true for everything, for the whole distribution. But the question is, why is Gauss's law true? The reason is that the way to think about it is that, say, start with the sphere. This is a cross-section of the sphere. Start by deforming the sphere by a small kink. So let me see, I deform the sphere by a small amount here. Just a tiny amount, a infinitesimal amount. So if I zoom out here, zoom this out, this looks something like this. A small kink in the sphere. So this can be deformed in an infinitesimal amount in a way such that this is the field E coming in. E. Such that the flux here is going to equal to the flux that was coming from this portion, right? And the flux on the walls of this deformation is 0 because this deformation is around the field lines. So the field lines here are parallel to the surface. So they won't contribute anything. And the flux coming out of here is going to equal the original flux coming out of the old surface. So there is always a way of deforming the surface and a small amount of time, given a small amount of this deformation, giving it a small kink, like, you know, it's this small deformation, in such a way, such as the deformation is around the field lines, such a way such that the walls of the deformation don't add to the flux. And then the flux after the deformation here in this part is going to equal the original flux that was here. If we deform the surface infinitesimally in this way, we don't change the total flux. But we can repeat this. I can keep doing that. I can apply a new deformation here. I can apply a deformation here. I can keep applying an infinite amount of infinitesimal deformations, an infinite amount of time, until I change the surface to something completely different. So I can go from this surface to this potato weird looking surface by applying an infinite amount of small, tiny deformations, right? So this ability to deform a surface into some other surface in such a way that every time you do this small deformation, you don't change the flux, leads to Gauss's law, leads to the result that the surface does not really matter. Its shape does not matter. This is a universal law, right? Just for a point charge. Now, why is this true for a distribution of charges? That is not a point charge. This is a distribution of charges, rho v, because of superposition. So Gauss's law is absolutely true for a point charge. Why is it true for a distribution of charges? Because of superposition. Because I can divide this distribution into point charges, and I can handle each point charge separately. Gauss's law is true for every point charge. So for the sum of charges, it's also going to be true. So this is true in general, not for a sphere. S could be anything. And Q could be any charge distribution because of superposition. This is Gauss's law. expressed in integral form. And this is going to be, so although we arrived at this result from Coulomb's law, we want to now step back and say, okay, I'm going to, Gauss's law is nicer than Coulomb's law. It's just something that's really nice. It says, I have a distribution of charges, integrate the flux of the field over a surface, any surface, and you get the total enclosed charges. So Gauss's law is a nicer result than Coulomb's law. So we want to start with Gauss's law. We're going to kind of say Gauss's law is the fundamental property, and Coulomb's law derives from Gauss's law. Right? So you want to take that point of view. And it's easy to see. I mean, for a point charge, you just apply Gauss's law, and you get point charge. I'm going to say Gauss's law is fundamental. So I'm going to say E dot ds over a surface, any surface, is going to equal Q, any surface, is going to equal Q over epsilon naught. So I'm saying this is the fundamental law of electrostatics. How can I spit out Coulomb's law from this? Easy. I assume the surface to be a sphere. If I assume the surface to be a sphere, from symmetry, because the sphere is symmetrical, the E field should be equal at every point on the sphere, right? So I can take it out, and then dot. So this is going to be E is going to be the magnitude of E times R hat. So E is going to be symmetrical. It's going to be just a function of R, right? So I can take this out. Integral of S R hat dot ds over a sphere. This is going to just be the surface area of the sphere. So it's going to be 4 pi R squared equals Q over epsilon naught. And this instantly gets me Coulomb's law. E equals Q over 4 pi epsilon naught R squared. And that's why we introduced the funny looking 4 pi into Coulomb's law. Because we were not thinking about Coulomb's law. We were thinking about Gauss's law as being fundamental, and then deriving Coulomb's law from Gauss's law. Okay. So this is what's called the integral formula for Gauss's law. We can actually represent Gauss's law in a different way, which is the differential form of Gauss's law. How do we get to the differential form of Gauss's law? We use the divergence theorem, right? So let me see. So the divergence theorem, right? So let's say I have a divergence. I can calculate the divergence. According to the divergence theorem, the volume integral of the divergence of E dV should be equal to the surface integral of E dot ds. But according to Gauss's law, we already know that this integral, the flux of E over any surface, is going to equal the total enclosed charge, E enclosed, over epsilon naught, or epsilon if it's some other medium. We already knew that. But what is the total enclosed charge? I can write it as a volume integral of rho V over epsilon naught dV. Right, the total charge is just the integration of the volume over the volume of the charge density. So I have two integrals that are equal. For them to be absolutely equal, their interiors have to be equal, right? Because remember, this has to be equal for any volume. Remember Gauss's law, this is a key concept. Someone might say, hey, what if rho V is different than divergence of E? But somehow the integration is, no, that cannot be true because this has to be true for any surface. That's Gauss's law that we proved conceptually. Because this has to be true for any surface, this has to be true for any volume. The only way this can be true for every volume is if the interior of the integrals are equal. So the only way this can be true for every volume is for divergence of E equals rho V over epsilon naught. This is not a new result. This is also Gauss's law, but this is what's called the differential form of Gauss's law. So the Gauss's law comes in two versions. It comes in the integral version and the differential version. But it's the same law. One is looking from the perspective of the infinitesimal, and the other one is looking from the perspective of the global. So if I talk about the postulates of electrostatics, postulate number one is Gauss's law, which comes in two versions. It comes in the differential version. If I zoom in and look at the microscopic, divergence E is rho V over epsilon naught. And it comes in integral version if I zoom out and look at the global picture. The global picture is that integral over a closed surface of E dot ds. I might have forgotten the closed sign. It doesn't matter. It's understood that it's closed. Equals the total enclosed charge over epsilon naught. Okay, so this is the first postulate of electrostatics. Remember Helmholtz theorem. It states that the electrical field, static electrostatic field, has a source that is the charge distribution. Right. Now the question is, could the electrostatic field have a vector source? Could a current lead to an electrostatic field? Something like a current, something like a vector source. It turns out, and this is the second postulate, which we also could prove in general, which is that I guess we can call it the circulation law. It doesn't have a name really. This is what I'm calling it, right? But just states that in differential form, it states that the curl of E is 0. So this is stating that the electrical field, electrostatic field, is irrotational. There are no current sources for the electrostatic field. So the curl of it is always going to be 0. And if you write it in terms of circulation, along the closed path of E dl is always going to be 0. The line integral along the closed path. So we can prove this result, I guess. I'll go through like a conceptual proof about it next time, but the key thing that this gives us, so the electrostatic field, what we can say about it, is divergent. It's not divergenless. It's non-solenoidal. Remember back from Helmholtz theorem. By the way, did we completely define the electric field in this case? Yeah, we did. According to Helmholtz theorem, we needed to define the curl and the divergence. It turns out for the electrostatic field, the divergence is there are sources for it that are scalar, which is the charge. So it has a divergence, so it is non-solenoidal. It doesn't have a curl, so it is irrotational. So it is a non-solenoidal irrotational field. It does not have vector sources like currents, but it emanates always from scalar sources like charges. And the beauty of this, because its circulation is 0, this allows us to express it in a different way. This allows us to express it using what's called the potential field, potential energy. And the only reason we can express it completely as a potential scalar field is because its curl is 0. So I'm going to go through this next time. Solve some problems. 1 minute. Any questions before we vamoose? So exam is still going to be, I'm going to submit it to Canvas early morning. Oh, sorry about the homework. I made a typo. I put the deadline March 31st. I hope you guys understood that that was a mistake on my part. I didn't assume that the homework is a whole month. So I put the correct date in. The midterm one, I'm going to post it Friday morning. It's going to be due sometime Saturday midday.